Section 14.1 involves a topic that's a weird mix of easy stuff and hard stuff. The easy stuff is the actual computations in algebra. There's very little solving equations or graphing or anything like that that's going to be happening here. The part that's hard here is vocabulary and notation. Just to begin, in the very title alone, when we call things sequences and series, those words in mathematics are used in a very specific manner, whereas in the English language, people are kind of sloppy and they use each word interchangeably with the other. In mathematics, a sequence means a list of numbers, just, one after the other. So something like 2, 4, 6, 8 would be a sequence. But in mathematics, when we use the word series, a series means you've added up the numbers from a sequence. So if you start with a sequence and you add up the terms, that produces a series. So series is kind of like the next step, and sequence is the starting point. And in this section today, and in 14.2, and in 14.3, we're going to always start by talking about sequences first, go through the formulas and techniques for sequences, and once we're pretty solid on sequences, then we'll talk about series next. That's the key idea there. The other key difference is that anytime you're talking about a sequence, like this one here, which, if you look at these numbers, it looks like these are the perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. When you have a sequence like that, there really isn't any reason you would expect it to stop at any particular point. Like, why did this one stop at 49? That seems just like a random decision to stop there for no good reason. Now, of course, in any practical problem where you're trying to do things, you'll always want to be working with a finite sequence. But in concept, really, most sequences should be infinite, because if you're going to list the perfect squares, don't they really go on forever? Isn't there really an infinitely long list of terms in this sequence? And although this doesn't seem like it's really a big deal that, yeah, you could, in theory, go on forever, when we get to section 14.3, the idea that a sequence can go on forever, it's going to come back around again, and it's going to be kind of important. These first few ideas here are mostly vocabulary things, and you can get the hang of that pretty quickly and without too much trouble. The part of this topic that's going to cause real headaches is the notation. When you work with sequences and series, we have this challenge where we want to be able to talk about different sequences, like there's this sequence, there's that sequence, there's some other sequence. So you would like to use a different letter for each sequence, but each sequence has multiple different elements in the sequence. So, for example, if you want to talk about the sequence A, you have to be able to talk about the first one that's in A, the second one that's in A, the third one that's in A, and so on. And the way we do that is with a little number down below called a subscript, and that number is called the index. So if the index is 1, you're talking about the first number in that sequence. The index is 2, that's the second number in the sequence, and so on. The part that really causes people trouble is when you're trying to come up with a formula that tells people if you want to find any term of the sequence, the 10th term, the 20th term, the 35th term, the 107th term, when you try to come up with a formula for that, you need a variable. You need a variable for the individual term you're talking about, and that is going to have to be the index. So you end up with what we might call the nth term. So notationally, that looks weird, and it causes people some headaches. But in terms of what you actually do with it, don't panic. It's actually pretty simple. If somebody says, find some particular term of the sequence, like let's just do the 7th. Find the 7th term of the sequence. Then this nth term thing is basically a formula, and you pretty much just plug into it. So you would take this here, and where there used to be an n, you would put a 7. And you would do that on both sides, just like you would when you're plugging into any formula. So here you would say the 7th term, a7, is 2 to the 7 minus 1, and then you do the arithmetic. 7 minus 1 is 6, 2 to the 6, your answer is 64. Same thing over here with this slightly more complicated formula. Don't panic when the formula is complicated. Just do the exact same thing you would do when you plug into any formula. First, plug in the number. That's a terrible one. Let me rewrite that. It came out kind of ugly. So let's see. 7 minus 1. And then 7 minus 1 is 6. 6 times 7 over 2, you can cross cancel there. 3 times 7, you're going to get 21. And then 5 minus 21, your answer comes out negative 16. So although the notation looks a little fancy or complicated, it's not really as bad as it looks. You're basically just plugging into a formula like we've plugged into formulas many times before. The part that really tends to throw people off is stuff like this, where we ask them to use the formula backwards, where instead of trying to find one particular term, we're asking them which term a particular number is. And so the idea is 256 the 7th term, or the 8th term, or the 9th term? Which term is it? So your answer here is going to be something like the 10th term, the 11th term. You're going to use like an ordinal number rather than a cardinal number. It's going to be slightly different vocabulary-wise. But the actual process is exactly the same as it was before. You've just got to be careful about where you plug certain things in. In this case, 256 isn't n. 256 is an. So in other words, that's going to go in to this part here. You're going to have 256 equals 2 to the n minus 1, and you're solving for n. Anytime the question says which term, your job is to solve for n. And then this here, this is a standard sort of exponential equation. You get a base of 2 on each side. Let me think, that's 2 to the 8th. And then you cancel the bases, and you get n equals 9. And make sure that because we are talking about an ordinal number here, you don't just say the answer is 9. The answer is actually the 9th term. So it's not 9. It's the 9th term. Which I know that's kind of a subtle difference, but it's really important to keep separate what number is in the sequence and which term of the sequence it is. Getting those two things confused is a really common mistake a lot of people make. Now, these examples I've been working here are examples where you have a formula for finding individual terms without having to build up to them. And that's not always the case. There's another type of sequence called a recursive sequence, where instead of having a formula that just says plug in n once and you instantly produce your answer, instead with these recursive sequences, you get something that's basically a recipe. And the recipe tells you how to cook up each individual term one at a time based on the previous ones. And a good way to think about this is, in this recipe, you could plug in different numbers for n. You could say plug in n equals 1, and then this recipe would say C2 equals 2 times C1 plus 1. In other words, for n equals 1, it tells you how to make C2. But then, if you plug in n equals 2, the recipe is, well, kind of the same, but it tells you how to get C3. And if you plug in n equals 3, it tells you how to get C4. And what we're hoping, us teachers, what we're hoping that you eventually get used to here is that the formulas, although they're technically different because you keep changing the index at the bottom, they're really kind of the same thing every time. They're always telling you, take the previous number, multiply it by 2, and then add 1. So yeah, the index changes every time, but there's not really a difference, an important difference, from one formula to the next. So using the green formula with C1 equals 5, you would get 11 for C2. And then you would plug that in here. 2 times 11 is 22 plus 1. You get 23. Then you would plug that in here. Let's see, 46 plus 1 is 47. Then you would plug it in here. Let's see, 94, 95. So when you're new to this, you plug in these n's and you work out these recipes and you plug the numbers into the recipes. But you shouldn't have to practice more than once or twice before you can just simply look at the original recipe here and understand what it's telling you to do. This is telling you take a number, multiply by 2, and add 1, and that'll give you the next number in the sequence. The other half of the topic here today in 14.1 is about series. And with series, what you're doing is taking a sequence, like the A sequence we had on the previous page, and you're adding up the terms. So if the question says, add up the first 5 terms of this sequence, that seems pretty straightforward. You're just going to say, okay, the first term, that's the second term, that's the third term, there's the fourth term, what's the 5th term? Let me think. If I plug in 5 for n, I get 5 minus 1 is 4, 2 to the 4, 16. And then, because it says to add them up, you would go in here and put plus signs all in between. And let's see, 8 and 4 is 20, or 8 and 2 is 10, 4 and 16 is 20, so 30 plus 1, you get 31. But you can see pretty rapidly that this is not going to be something you want to do in general. Like this here, add up the first 53 terms of this sequence. Is this something that you would imagine somebody would want you to do by hand? Of course not. Of course not. What we do instead is we use formulas for that kind of thing. And the problem is that for different types of sequences, we have different types of formulas. Today, we're not really going to have any formulas because right now we're considering just sequences and series in general. But in 14.2 and in 14.3, we're going to talk about specific types of sequences. And each particular type has formulas that go with that type. So, yes, we use formulas, but unfortunately there's no one formula that works for every series ever. Instead, what we need to do today is build up the notation so that we can talk about the formulas. One kind of notation is this sort of thing, where if you're adding up the terms of a series, the total you get has its own special name. We call that Sn. Anytime you see a big capital S with a subscript n, what this is saying is the sum of the first n terms. So you start with the first term, take the second term, and so on, and you stop when you reach n. One thing that's a little tricky about this is you have to realize that there's really 2 different variables here. One of the variables is this index changing from 1 to 2, 2 to 3, 3 to 4, and so on and so on and so on up to all the way through these numbers. And then the second variable is, where do you stop? Do you stop after 5 terms? Do you stop after 53 terms? So there's really 2 variables in here, and that's one of the weaknesses with this capital S notation. So there is a more complicated notation that we often have to use because it contains more information. This here doesn't contain enough information. So the more complicated notation, it looks like this. And as you can see here, it's trying to communicate the same idea, add up the first n terms, but it has some things that are different. It's got two variables in it. The k is the part that changes from here to here to here to here. It's the index. It goes from k equals 1 to k equals 2 to k equals 3, and so on and so forth. So the k is the index that's changing from 1 all the way up to n. And then n, that's the last one you would stop on. That would be like you stop at the 5th one, or you stop at the 53rd one. The other thing that's an advantage about this notation is this part here. This is where you can put the formula for the terms. And if you think about it, that's one of the biggest problems with the capital S notation we have up above. The capital S notation, it just says add up the first n terms of the sequence, but you don't necessarily know what sequence they're talking about unless you look somewhere else to find that information. Here, the formula for the sequence terms would go right there, and you would know precisely how to find the terms. So let's do an example of this, because this part here is probably the toughest thing you're going to see in 14.1. Not because the actual work is all that difficult, but because it's notationally complicated to figure out what you're supposed to do. So let's do this example here. Notice how this works. This piece here, this is the formula for the terms. We're going to be plugging into this to figure out what the various terms are. And then you'll notice down here at the bottom, it's possible to start somewhere other than with the first term. This part here is basically saying start with k equals 3. So what's the 7 up at the top doing now? Well, it still means that's where you end. So we're going to end at k equals 7. Here's how I suggest you work this problem out. Write out the k's you're supposed to be working with. So we start with k equals 3, and k is the index. It's going to go to 4, and then 5, and then 6, and then 7, and when you get to the one you're supposed to stop at, stop there. That's your first step. Just list out which k's you're going to be working with. And then for each individual k, plug it into the formula. So you would have -1 to the 3 plus 1 times 1 over 3 times 2 to the 3. That's what you get when you plug in 3 to the formula. When you plug in 4 to the formula, you get -1 to the 4 plus 1 times 1 over 4 times 2 to the 4, and so on. -1 times, or to the 5 plus 1 over 5 times 2 to the 5, -1 to the 6 plus 1 over 1 times 6 times 2 to the 6, and then this last one would be -1 to the 7 plus 1 times 1 over 7 times 2 to the 7. So each individual one of those takes a little bit of arithmetic, so don't try to do them all at once. Take them one bite at a time. Work out each one individually. Like this first one here, 3 plus 1 is 4, -1 to an even exponent comes out +1, so we're basically just doing 1 times the fraction. 2 to the 3rd is 8 times 3, we get 1 over 24. Then shift your attention to k equals 4. 4 plus 1 is 5. -1 to an odd exponent comes out -1. So we have -1 times this fraction. Denominator there comes out to be 64. And so on. You work out each one. Here we have an even exponent, so it goes back to positive. By the way, that -1 with a increasing exponent thing, that's a pretty common piece of series that you're going to run into. It's basically a way to make the series switch from positive to negative to positive to negative to positive to negative. It's called an alternating coefficient because of that behavior that it does. And that ability to make your terms switch from positive to negative is why it's pretty common. So as you go through here, our terms are switching from positive to negative to positive to negative, and the denominators are getting bigger and bigger and bigger, And you're looking at this and you're realizing, man, that looks like a lot of work, especially once you realize, oh yeah, we're supposed to add up all of these things. It's a series after all. But then notice what the directions said, way back up here. Round to 6 decimal places. So at this point, don't panic. You just grab a calculator, you type in that sum of all those fractions, and you end up with 0.0308035714, blah, 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 blah. And you round to whatever number of decimal places you're told to round to. So in this case, if we're rounding to 6 decimal places, you'd have that. So make sure you practice this notation here. It's called, by the way, sigma notation, because this Greek letter here is the Greek letter sigma. And sigma is, strangely, the historic ancestor not of the letter E, but actually of the letter S. So it's kind of like the Greek letter version of the notation we had above it. Practice this stuff. This stuff is going to be the trickiest part of 14.1. And once you learn how to read the notation, the actual process is just really working out the arithmetic. You don't have to solve equations or anything. It shouldn't be too